Now, suppose we have a random variable x with probability mass function f of x, given the probability that x is equal to some value. The cumulative distribution function, CDF, is a function that gives us the probability that x is less than or equal to some value. Before we find cumulative distribution functions, let's consider some of their properties. So let f be the CDF for some random variable x. Suppose x is less than y, and consider the events our random variable is less than or equal to x, and our random variable is greater than x but less than or equal to y. These are mutually exclusive, so the probability that x is less than or equal to y will be But since the probability of any event is non-negative, this means that the probability that x is less than or equal to y must be greater than or equal to the probability that x is less than or equal to x. In other words, f of y must be greater than or equal to f of x. And consequently, the CDF for a random variable is a non-decreasing function. Moreover, since a probability must be between 0 and 1, and the cumulative distribution function is the probability of some event, then f of x must also be between 0 and 1. There's one last feature of a CDF if x is a discrete random variable. Since x is discrete, consider any two consecutive values of x, say I and j, and consider some value x between the two, strictly greater than I and strictly less than j. So our cumulative distribution function, that's still the probability that our random variable is less than or equal to x, but because x is between I and j, we can split this into two mutually exclusive events, x less than or equal to I, together with x up to the value of x. And because these events are mutually exclusive, the probability of the union is the sum of the probabilities. But because x is discrete, the probability that our random variable is between these two consecutive values is 0. And so we're just left with the probability that x is less than or equal to I, which is just f of I. Consequently, our CDF will be constant over the interval starting at I up to but not including that next value. This means that for discrete random variables, f of x will be a non-decreasing, piecewise continuous step function. And again, it means that if I and j are consecutive values in the range of x, then f of x will be constant over the interval starting at I up to but not including j. So now suppose I and j are consecutive values in the range. How does f of I differ from f of j? So we note that f of j is the probability our random variable is less than or equal to j, and again we can split that into a union of events which are mutually exclusive. So the probability of the union is the sum of the probabilities. The probability that we're in between I and j is again 0 because we're assuming I and j are consecutive. The probability that x is less than or equal to I, well, that's just f of I. And then we have this probability that x is equal to j. Consequently, our discontinuous function is going to jump at the possible values of our random variable, and the size of the jump corresponds to the probability of that value. And this allows us to construct some CDFs. So let's consider a fair six-sided die, find a cumulative distribution function for the numbers shown on the die. Since the possible values are 1, 2, 3, 4, 5, 6, then the function is going to be defined over 7 intervals. The intervals beginning with and including one of these, and ending with but excluding the next. And then there are these additional intervals that you can think about as the remainder, since our function should actually be defined for all x. So we need something before that first interval and after that last interval. Since the probability that we get a particular number is 1/6 for any of these, then the cumulative distribution function is going to jump by 1/6 at every transition. So we start at 0, add a 6th, 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 add a 6th. And there's our CDF. We can also go backwards. Suppose f is a CDF for some discrete random variable. We know that f must be piecewise constant, where f of x is some probability. We can recover the probability mass function by noting the interval boundaries xi form the range of x. They're the possible outcomes. And the difference between consecutive values of our CDF is going to be the probability of the boundary. So, for example, let's suppose we have a CDF. Let's recover our probabilities. So note that the interval boundaries occur at 1, 5, and 6. So x, the outcome, could be 1, 5, or 6. But since we're working with a discrete probability mass function, it couldn't be anything else. So the probability that x is equal to x is going to be 0 if x isn't one of these values. Next, we note that the probability that x equals 1 is f of 1 minus f of a, where a is any value less than 1. So that's going to give us probability. Next, at our second value, x equals 5, our probability is going to be the difference between the consecutive values, f of 5 and f of 1, which will be and finally at 6, our probability will be the difference between the consecutive values, which will be